The main widget that gets added to viewports on startup in our UI setup is our UI material labels canvas, and I've done a bit of spring cleaning. I've actually brought in the quadrant graphics, just copying and pasting them between those two widgets so that I didn't have to create another widget and add it to the viewport for just the visual elements. So in here are our visuals and our blueprinting that is handling the creation of the child actors depending on how many markers there are in the world, and then running through each of those elements. So let's just look at the child widget before we start diving into the main labels canvas. So what I've got in here is pie small, medium and large in a small widget of 250 pixels each, with the anchor set to the center. The other thing to note is that I have got now a material dynamic circle on both the small and the medium, but then on the large I've retained a large circle material because that is the material that I'm still using the material parameter collection to drive the scale of the widget when it hits the boundary. So that's all that's in there. There's nothing in the graph itself. So coming back to the canvas, let's see what's going on here. In the world, we have one of our markers spawned and connected to a socket, and then a second one I've just dropped into the world. So no matter how they get created in the world, on event construct in our labels canvas widget, we're seeing how many are in the world and adding those into an array. And then for each of those actors in the world, we are creating our child widget. Once we've created, in our case, 2, for each of those widgets that we create, add a child to the canvas, and our canvas is just our canvas panel 0 here. So 2 get added, and while we're there, we're also putting them from the return value pin into a pie widget array. So we've created them and we've added them as children to our canvas. So on tick, then we're taking that pie widget array, we're running a for each loop based on the length of that array. So in our case, twice. We are doing the following. So we've obviously got a few options that we're going to cover. At the moment, I've got the quadrant condition hooked in. So every time we pass that center line, we're offsetting the position. So the first thing that we're doing in our sequence, after we've stored our array index, is we are saying that if our child on screen position at any point, remembering this is on tick, is under 960, the center of the screen, then to set the offset amount. And this offset amount gives me control over how far I want the child widget to be from the mouse location on the screen. So I can kind of tweak that. So I'm offsetting it positively or negatively by timesing it by -1, depending on whether it's less than or more than 960 pixels on the X screen position. So then I'm doing exactly the same thing for Y, but our center line is at 540 because we're working on a 1920 by 1080 screen. That is hard-coded here because I'm working to that screen size, but you could take the screen resolution and then just divide it by 2 to work out the half, so that when the project launches on different screen sizes, it's always the center line that is the tipping point for true or false. So we're defining what that offset is. And I've just hooked it in here. Should I want to increase the amount of offset, I'm only doing it in one place and it's then automatically recalculating it. If I change that variable here, I've currently got that set to 135 pixels as the offset. We'll do that first. We probably don't need to do that in the for each loop. We could do that here so it doesn't fire twice. Anyway, it is no big deal in the prototype, but it's just good to always review what you've done. Then, pin 2 on our sequence. We're setting some local variables where we're getting, again, on a per instance basis, the label marker actor world location, and we're projecting the world location to the widget position. That's how we translate a world location to a screen position. And then I'm just writing out the X and the Y locally here to avoid some spaghetti down the line. Now, when I first hooked that up, there was some weird offset happening that I've just put in this correction. Now, I'm having to -50 and -16 on the X and Y respectively for the widget to appear under the mouse position, which I was using to debug the alignment. Is it something to do with the DPI of the screen? That's what I think it is. This works, but I can't fathom why it's 50 and 16. My child widget is 250 by 250, so there's no kind of logical correlation of where that 50 and 16 come from. So, something I need to crack or understand, so if you do know, let me know, please, in the comments. What we are then doing is we are getting the slot position of our child, and we are basically getting its current position and defining what the new offset position should be, on tick, remember, and we are just using an finterp node to tween between its current position and the new one. So this constantly updates. As I'm moving the widget around the screen, the target is constantly updating, hence the tweening catches up. Now, we've got control over the interp speed, so you can make it snap much quicker. I've got it quite sort of fluid at the moment, but this is the value that you can kind of tweak to affect the responsiveness. So what I've done here, if you recall, I'm taking the return value from our tweening, but running it through a clamp. Now, our borders that it's hitting is 200 pixels all the way around, but I'm having to apply this offset again here, hence the 150 and 1670. Because we have a screen width of 1920 pixels, but I'm having to take away 50 from that one and add 50 from that one. So rather than it being 200 and 1720, which is 200 pixels in from 0 and 1920, that offset gets reapplied and then it works. So exactly the same thing for the Y. So if I don't want to constrain within the limits, I'm quite happy for my widget to go off screen, I would just miss that clamp, basically, and just skip it. So it's only those nodes that are doing the constraining. Then what I am doing is for each of the images in our child widget, pi small, medium, large, I'm getting the dynamic material for each of those images and saving them out as local variables. And the new material that is part of the small and medium circles, I've taken out the material parameter collections that I had in there and added 2 new scalar parameter values. So I've got dynamic radial here, and I've got dynamic scale here. So just those 2 scalar parameters have replaced the material parameter collection, so that now we can deal with this on an instance by instance basis. So that's the same for small and medium. You can see here dynamic radial. And I am using a map range clamp node to get the screen position, our X in this case, which we know is within a range of 0 to 1920 pixels across, but I'm remapping that to 0 to 1 because the dynamic radial in our material works on a 0 to 1 scale. So if I come in here and I put 0 in, it disappears. If I do 1, it fills completely. 0.25 is a quarter. So that's why I'm remapping it using that map range clamped node. I love these nodes. They just take the guesswork out of a lot of it, or the complicated maths of doing it. So these are designed to make your life a lot easier. I'm doing exactly the same thing for the medium pi image, which is representing the Y location. But for the large image, I am creating the dynamic material, saving that, but then I'm still using material parameter collection to drive the scale of the RPM gauge. So just to show you that, you know, you can have some things local, or you can have a material parameter collection driving something universally if multiple instances are referring to that same scalar value. So that's just to show some variations on a theme. And then I have a branch here which is handling my scaling, which is basically saying if our X position, I can probably, let's get rid of that spaghetti here. I tend to stack. I like stacking things. I can kind of read them logically. I don't like that particularly, but that'll do for now. So on my branch, I'm basically saying if my X position is less than 300 but more than 1620, or my Y position is less than 300 pixels or more than 760, i.e. the boundaries that I've created to trigger the scaling. So if any of those conditions are true, then I'm doing the same thing for small, medium and large here. I'm taking our material instance dynamic, which we created here, and then I'm just getting the scalar parameter value, which is currently, and then I am using an finterp2 node to basically scale down. So I'm now going from 0.2 on the dynamic scale. So in here we had our dynamic radial. Our dynamic scale in here is just dealing with scaling. So if it's true, I'm scaling down to 0.2, and then if it's false, if any of those conditions are false, i.e. the child widget is within the border boundaries I've set there, then just scale it back to 0.5. So that's absolute rinse and repeat for small, medium and large, just making sure we are using the dynamic scale, the parameter name field, and then obviously here we had dynamic radial. So that is doing all of that. So let's have a look at the variations. Now I've just gone and played the preview and something had broken, and I basically become a victim of my own assumptions. So the best saying that I've ever heard is, assumptions are the mother of all fuck-ups. So that's certainly what happened there. If you recall, I was coming out of here and writing these two local variables. Not very helpful when I'm trying to reference them before I've even set them. Not necessarily a problem on tick, because it will kind of catch up eventually, but it didn't work. It's not what I want. So let's now have a look at the amends that I've made. I'm going to get rid of those local variables. I'm just going to plug straight in from our project world location to widget position node. This is the quadrant condition, so let's have a play of that. So you'll now see for each of the pie charts, when I cross the quadrant, it's moving the child widget up to the opposite corner. So that's happening on both. You can see that. So that's great. Let's have a look at our condition, which was for just the border based on 100 pixels. That's the only difference, is that I'm just basically saying within our 100 pixel border. So 100 pixels is this first line, 100, 100, 100, and 100 from the 1080. So now when I cross that line, because I've got the constraint on, you can't see that because the constraint is up to 200 pixels. Let me do something there, and rather than having two separate values, let's change that to 200 and 200, and then at least we're now working with the same inner boundary. And in theory, when I move to the left, this will reposition to the right hand side when I go across this line here. There we go, it's pushed it out. It's within 300, which determines my scale threshold, because I've got another threshold here which, when I'm beyond this line, it scales down. So when we come out of that, it scales up. So that's basically working for the, so if we look at this one now, when I cross the line here, this will position down. And so yeah, it just pushes it down. So that is the condition for the border. And then I am going to unplug these offset. And then I am going to just in case that local variable is the problem again, I'm just going to go straight from our node there and then plug that in as the addition for X and Y, which is using the map range clamp node again for the width 0 to 1920, which is ascending, and then swapping it to a descending range of 200 to -200. So it's 400 pixels, which is handling that positive or negative offset based on the marker's projected position on screen. Let's see if I've done it correctly. And now with this version, the widget should always be relative. It's not being triggered by any quadrants. So if I come to the middle of the screen, there should be no line, basically. So yeah, it's relative now. But when I come over here, the distance of that line increases depending on how far I am from the center. So that is the kind of relative. We're still using our boundary. And just to demonstrate that it can take something as simple as a single node to change the effect of something, I'm going to bypass the clamp so that the widgets can now break the border, basically, because that clamp has been removed. So when I move the markers off screen, they'll still shrink down after that 300 pixel boundary, as we can see here on the right and left now. But if I go off screen, they're no longer constrained to the border. Single node handled that constraint. It's brilliant. I love it. And let's have a little play around with that interp speed. If I make that 5, for example, now our child widget is going to be much more sticky. So it's moving around very quickly. Repositioning. That's probably a bit better actually. It was a bit floaty before. So yeah, there we are. So I hope that video is of use. If so, please do like and subscribe and hit the notification bell to receive any updates. And thank you for your support.